In some sense, the derivative can be thought of as zooming in, examining how we can make small changes in a function just by tweaking its input. But now, it's time to introduce the other big concept of calculus, where we'll zoom out and accumulate those changes together into an overall whole. It's time to introduce the integral. Ever gotten stuck on a really hard problem, math or otherwise? It can be frustrating when you've tried everything you can think of, but nothing seems to work. It happens to the best of us. And according to legend, it happened to one particular Archimedes of Syracuse. He'd been asked to find whether the king's crown was made of gold or some lesser metal. He knew, based on his understanding of science, that he could weigh the crown, then divide the mass by the volume to find the density. He could then compare that with the known density of gold. Problem was, the only way he could think of to find the volume of the crown was to melt it down. Which is kind of a problem, because if it really is made of gold, then you've just melted the king's gold crown, and he's not likely to be happy. Archimedes puzzled over what to do, getting more and more frustrated, until his wife suggested he take a break from the problem. Take a bath, she said, and your mind will be refreshed afterwards. And that's what he did. But when he got into the bath, he noticed that the water level rose. And he realized in a flash of insight that if he put the crown in water, he could measure how much water was displaced, and that would tell him the volume of the crown. Now I say flash of insight because the next thing he did was jump out of the tub and run down to meet the king, yelling "Eureka," which is Greek for "I found it," all while having forgotten to put clothes on. So the moral of the story here, besides not running naked down the street, is that taking a break from a problem can sometimes lead to better insight than just banging your head against it repeatedly. And it establishes an interesting side note, which is that apparently there's a history between mathematicians and bathtubs. In fact, let's suppose you decide to take a bath. You could just turn the faucet on, wait for the tub to fill up, and then turn the faucet off. But you decide to do something more interesting. So you turn the faucet gradually, linearly in fact, so the water pours out faster and faster. 1 gallon per minute, 2 gallons per minute, 3 gallons per minute, and so on. By the time you've reached 10 minutes, the water is pouring out at a rate of, say, 6 gallons per minute. You quickly shut the faucet off and get into the tub. As you relax in the hot water, you find yourself wondering, how much water did you pour into the tub over those 10 minutes? And you begin to ponder. It's time to introduce another useful technique in mathematics, coming up with bounds on your answer and then refining those bounds. How can we come up with lower and upper bounds for the amount of water in the tub? Well, to start off with, we certainly know one good lower bound: 0. If we'd never turn on the faucet at all, we'd have 0 gallons of water. And negative volume doesn't make any sense anyway. Okay, what about an upper bound? Remember that at the very last moment, just before we shut the faucet off, the water was pouring out at 6 gallons per minute. Before then, we were building up to that rate gradually. But if we'd gone straight to 6 gallons per minute from the very beginning and kept it at that rate for all 10 minutes, we'd have 60 gallons in the tub, assuming the tub is big enough. It intuitively makes sense to multiply the rate by the time, and the units check out. Gallons per minute times minutes indeed gives us gallons. So we know, at the very least, that there have to be between 0 gallons and 60 gallons of water in the tub. But that's a pretty wide range. Can we do better? Well, we could refine our estimate by breaking up the problem into 2 sub-intervals of 5 minutes each. Then we could run our same analysis on each of these sub-intervals. During the first 5 minutes, the water ramps up gradually from 0 gallons per minute to 3 gallons per minute. So that tells us that during that time, we gained somewhere between 0 gallons per minute times 5 minutes, and 15 gallons, 3 gallons per minute times 5 minutes. Then, during the next 5 minutes, the water ramps up gradually again from 3 gallons per minute to 6 gallons per minute, which means that during that second interval, we gain somewhere from 15 gallons, 3 gallons per minute times 5 minutes, to 30 gallons, 6 gallons per minute times 5 minutes. So combining our lower estimates and our upper estimates, the total amount of water in the tub has to be between 15 gallons, 0 plus 15, and 45 gallons, 15 plus 30. To recap, what we've done here is multiply the minimum and maximum rate at which water is flowing on each subinterval by the length of that subinterval, which in this case is 5 minutes. Wait, if we were able to refine our bounds by cutting up our problem into subintervals, could we do it again and get even tighter bounds? Let's try it. In fact, let's divide things into 10 intervals of 1 minute each. We could look at the minimum and maximum value of our flow rate on each interval and multiply that by the length of the interval, which in this case is 1. If you work through the calculations, this narrows things down even further. The amount of water in the tub is now between 27 gallons and 33 gallons. We're really getting somewhere now. Now, we could keep going with this process, getting tighter and tighter bounds by splitting our interval into smaller and smaller pieces. The only problem is that every time we do that, we have to do more and more calculations to get our answer. So this is where we might want to take a step back and try to get some insight into what's really going on. What we've been doing is repeatedly multiplying the rate by a change in time, the length of our time interval, and then adding up all of these products over the full 10 minutes. Now remember, a great way to visualize multiplication is with the area of a rectangle. And as you might have noticed, we've been splitting up our graph into rectangles to show the minimum and maximum rates. And then the area of each rectangle is in fact the rate times the change in time. So that rectangular area tells us how much water is poured into the tub during any given time interval. Then, as we made our intervals smaller and smaller, our rectangles get thinner and thinner, and we get tighter and tighter bounds on our answer. So bear with me here. What if we somehow made our intervals infinitely small and used infinitely many of them? Ideally, that would make our upper and lower bounds infinitely close together, so close that we essentially couldn't tell them apart anymore, and we'd have the true amount of water in the tub. Visually, you could imagine that if we used infinitely many, infinitely thin rectangles, those rectangles would hug our function infinitely closely, and the total area would be indistinguishable from the area under our graph, in this case a triangle. If we find the area of that triangle, 1/2 times the height times the base, we'd have 1/2 times 6 times 10, which comes out to 30. That means that in fact we poured 30 gallons of water into the bathtub. So let's sum things up here, so to speak. What we found is called an integral, more precisely a definite integral. And the process of calculating an integral is called integration. We also have a special notation for it. We use a long letter S, which stands for sum, but a smooth sum, as opposed to the piece-by-piece jagged sum usually expressed with the Greek letter sigma, like we saw earlier. We put the start and end of our interval at the bottom and the top of the S. Here, that's our start and end times, 0 and 10 minutes. What comes after is our function times an infinitesimal width. In other words, it's the area of that infinitely thin rectangle. Here, our rate function is r of t, so that infinitesimal width is dt, just like the d we used for derivatives. It's a differential. So by harnessing the power of the infinite and smoothly summing those infinitely thin rectangles, we get the total area over our interval, and that area represents the accumulation of a rate, tiny bit by tiny bit, resulting in an overall amount by which the whole thing has changed. As for units, each rectangle's area is measured in gallons per minute times minutes, which is gallons. So when we add all of those rectangles together, even though they're infinitely thin, our final answer is still in gallons. Now keep in mind, I haven't actually given you the full definition of an integral yet. This has been just a particular example. There's one more thing we need to look at first. Okay, suppose at the end of your relaxing bath, maybe 40 minutes after you first turn the water on, you pull the plug and let the water drain out at a constant rate of, say, 5 gallons per minute. So it'll take 6 minutes to drain the whole tub. Could we still use integration to talk about the change in water volume? Well, we could treat draining the water as a separate problem, but that's kinda clunky. Instead, let's do something a little more elegant. Let's treat that as a negative rate of change for the volume. In that case, over those 6 minutes, the overall change in water volume should be negative 30 gallons, the amount of water decreased. So that suggests that we should treat this rectangle under the horizontal axis as if it has a negative area. What? Negative area? How's that possible? It seems weird at first, but remember, we have a real-world meaning for it. It means we're losing water. So now that we know this, we can finally define our integral and make sure to take this into account. The definite integral of a function f of x over some interval is the signed area between the curve and the x-axis. Signed area means that area above the axis counts as positive, and area below the axis counts as negative. The key intuition to make sense of integration, especially for real-world situations, is accumulation of tiny changes. And if we think of the function we're integrating as a rate, positive area means we're gradually gaining something, and negative area means we're gradually losing something. We can always be flexible with making definitions like this, if it gives us a better sense of what's really going on. Finally, since the integral is all about accumulation of tiny areas, it should be reasonable that its units are just the units of the function times the units of the independent variable. Remember, area is a product, so we have a product of the units. Now there's an important note to make here. In our bathtub problem, we were lucky enough to be able to use basic geometry to find our areas. We had a triangle and a rectangle. But that's not always the case. What if our water volume was changing at a rate more like this function? If there's a nice clean area formula for this shape, I certainly never learned it in high school geometry. We'll learn how to deal with this case soon. Though, if you're just itching to know an answer, you can use technology to find the integral, just like with derivatives. For example, if you go to Desmos and type out int, int, it'll create that nice smooth S symbol for you. Fill in all the pieces, your left and right endpoints, the function you're accumulating, and don't forget that infinitesimal width at the end, dt, and you can find any integral you'd like numerically. Okay, this is all well and good, but there's one thing you might still be thinking. All this talk about infinitely many, infinitely thin rectangles. Is that really possible? How do we know this actually works? Those are valid concerns, which often come up anytime you deal with the infinitely large and infinitely small in math. Just like with derivatives, we'll address those concerns once we're ready for them, once we've introduced limits. But for now, it's okay to trust that integration works the way we intuitively feel like it should for any situation that we'll ever run into. And it's also kind of worth marveling at the beauty of just how well this worked. Infinity is a powerful concept, and calculus really taps into its potential. Eureka indeed.